The support vector machine, of which the support vector classifier is a particular instance, is a discriminative method. And I think it is fair to say the most fashionable method of the last decade. So there was a huge burst of research into the field starting in the late 90s, and it has really dominated the field for a decade or so. Now, the way it's presented, usually, I think some of the implicit assumptions are not really made clear, and I will start very slowly by trying to point out each and every one of the arbitrary decisions that go into the design of the support vector machine. And I will start by giving a pretty careful discussion of loss functions. So loss functions are a measure of empirical error, where empirical error is defined as the error that your classifier makes on the training set. That is, as opposed to the generalization error or the error that you measure on an independent test set. Now, the ideal loss function would have the following properties. It would be convex. That makes for easy optimization, simply because convex problems are so much easier to optimize, and what's more, it has a unique optimum. That is important if you remember when we discussed neural networks, or what you've seen in the exercises, that there are so many local minima, and it's a matter of luck of finding a good or a deep one. And if you have a convex problem setup, you're guaranteed to have a unique, well, you're guaranteed to have an optimum. It need not be totally unique in the sense that you could still have a basin that is flat at the bottom, but at least you will have just a single basin. Then secondly, your ideal loss function should be robust to cope with outliers, which you always expect to see in your data in the real world. And finally, you would like it to give sparse solutions. Actually, there are two notions of sparsity. You can have sparsity in the primal domain or in the original feature space domain. Sparsity in the primal domain would mean that not all features are needed to specify the decision boundary, or in other words, some of the features would be redundant. So the decision boundary would be parallel to some of the dimensions. So if we look just at a two-dimensional feature space, x1 and x2, those are the coordinates. If I have a decision boundary like this, you see this depends only on x1 and not on x2 at all. So that would be a solution that's sparse in the sense of requiring only specification of one of the two features. And same or similar concepts hold for higher dimensional feature spaces. Or you can have, and that's more what's meant in the context of support vector machines, you can have sparsity in the dual, where it means that not all samples have an effect on or are required to specify the solutions. To specify the optimal solution, and this should become clearer later on. Now, I would like to do a case study here, a case study of different loss functions. I've plotted a couple of loss functions here and 2 toy problems. Now, there's a lot of information on this sheet, so we will spend quite a bit of time on it. Let's start with the 0-1 loss. So the 0-1 loss is shown here by the black line. It has this step function shape, and I've plotted this as a function of the label, which is assumed to be either -1 or +1 times the normal vector of your classifier. X is your query location, and B is a bias. So, in other words, if we have a coordinate system, let's say let's say that this is my linear classifier, and I specify this classifier on the one hand with a normal vector, and here I'm using a normal vector W tilde, which I assume to have unit length, and if it has unit length, then the bias B or minus B measures just the distance of this linear surface of this hyperplane in higher dimensions from the origin. Now, I want all samples of the positive class, of the class +1, to lie on this side, and I want all samples from the negative class to lie on the other side. And if I consider this position here, so X times W, that would be a positive number. B in that case would be a negative number. So all samples lying on this side of the decision boundary result in an overall positive number. And if I multiply this with a +1, I get out a positive number. So this is the score that I've been plotting here on this first axis. Whereas all samples lying on this side of the decision boundary, they have a negative score, and if I multiply this negative score with the negative label, I again obtain something positive overall. So I'm on this side. And the 0-1 loss is just this step function here. So the 0-1 loss means whenever I'm on the right side of the decision boundary, I incur no penalty, I incur no error, and if I'm on the wrong side of the decision boundary, I get a constant penalty or error of 1. I have a constant loss of 1. So I'm collecting a couple of properties here, starting with the 0-1 loss. It is, unfortunately, not convex. So convexity is the following property. I'm looking at, I'm plotting 2 functions here. Let's say this would be a convex function. And then I have a second function here, which is not convex. This function here is convex because I can connect every point to any other point without ever cutting the function. And this is true for some of the points on this function, but not for all. So for example, if I draw the second from this point, let's say to that point over here, you see that I'm crossing my function, and that's why it is not convex. And well, for these reasons, the step function which I've plotted above is also not convex. So if I take this pair of points, it would be okay. But if I use that pair of points, I'm cutting the function here. So this is not a convex function. So in other words, using the 0-1 loss does not give us a unique minimum, and this is already something that we saw last week when we talked about the perceptron. And well, let's look at these two toy examples. I have a one-dimensional feature space X here, and on the left-hand side I have a linearly separable training set. So the circles are the negative class, and the crosses here are the positive class. And in this case we have a toy example that's not linearly separable. Again, the circles and the crosses, and you see that there's no perfect classifier here. Now, the empirical loss has now been plotted for all these loss functions, and you see that the black line, this step function here, the black line is the empirical loss for this data set here. And you can glean a few properties from that. So since it is piecewise constant, we cannot use any gradient descent type of techniques. Also, in the non-linearly separable case, we get local minima. So even for a very small example like this one here, we have a local optimum or a local minimum here, and then another local minimum there, and finally another local minimum up there. And well, since there are plenty of steps here, it is definitely true that the resulting loss function is not convex. So for all of these loss functions, we accumulate the total empirical loss from contributions from the individual observations. And if, well, one function in this summation is not convex, then the entire sum is also not going to be convex. So it is not convex, but on the positive side, it is robust, because you see here, if a sample lies on the wrong side of the decision boundary, we get a penalty of 1. And if the sample lies much, much further on the wrong side of the decision boundary, the error is still just 1. So the error does not grow in any steep way, and that means it's not going to distort your classifier. It is robust, and that's a good thing. Also, it is sparse in the sense that the empirical error here goes exactly to 0 for all samples on that are correctly classified. This is the reason why in the perceptron training algorithm we only had contributions from the misclassified samples. The positive samples here, they leave the decision boundary alone, and in that sense it is sparse in the dual domain, or it will lead to sparse classifiers in the dual domain. However, unfortunately, you also see that there's some ambiguity here. So we have ambiguous optima, and what I mean by that is that in this case here, so again, the step function here, the black step function, shows me what the empirical error is as a function of where I put my decision boundary. So if I put my decision boundary here, the empirical error would be 3, 2, 1. And if I put my decision boundary anywhere in this region here, the empirical error will be 0. And, well, that is not so nice, because you would ideally, you know, if you give this training set to somebody, or if you give this training set to 10 people, and if you give that loss function to 10 different people, and these people are computers, let's say, you would like to get out the same solution from each one. And here, there's no way to discriminate which of these solutions is the best one, because they all have this empirical error of 0. Now, you can think of obvious ways of lifting this ambiguity, and this is just what the loss functions that we're discussing now are trying to do in different ways. So one way to reduce this ambiguity is actually to use this shifted margin. So that's plotted very, very faintly. The shifted margin is also a step function, but it has its step over here, okay? And so we already have an error, not just if a sample lies on the wrong side of the decision boundary, but if a sample even comes close to the decision boundary, it already gets an error. And this results in this dotted loss function that you see here. And you can see that the range of ambiguity has now been reduced. So this space of solutions that all have zero empirical error, which is, by the way, also called the version space, using the 0-1 loss, it went from this point to that point. And now if we use this shifted 0-1 loss, we've reduced the ambiguity from here to there. And if we kept shifting this loss further, we could even reduce this ambiguity until we're left with just a single point. And that it gives rise to an optimization problem very similar to the one that we're going to solve later. Okay, so that was the 0-1 loss, and what we've discussed just now was the shifted 0-1 loss, or you could say the 0-1 loss with a margin, and it inherits the same properties of being not convex, of being robust, of still being sparse, but it reduces the ambiguity. So it's as above, but entailing less ambiguity. Then also last week when we talked about neural networks, we talked about sigmoids. So for sigmoid loss functions, and I've plotted a few. I've plotted two sigmoids here. One was pretty steep, and the other one had a smaller slope. They mellow out the 0-1 loss, and they are still not convex. However, they're still robust. If they're sparse or not, it depends on the exact formulation that you use. So for example, if you obtain this sigmoid by convolving your step function, say with a B-spline, so with some smoothing kernel of finite support, then you can still obtain something that is sparse. But if you use something like the logistic sigmoid, then you have a function that only approximates 0, but it does not go quite to 0. And that's what's typically used. So I would say it's usually not sparse in the dual domain. Because even observations that lie on the correct side of the decision boundary, they still contribute a little bit to the loss. So if you want to minimize the loss, in a way your decision function still feels the influence of the samples, even of those that lie far on the positive side. It's not a strong influence, but it is there, and unless you truncate it, it means that the decision boundary will depend also on the exact location of all the samples on the correct side, and this is why I'm saying that this is not going to give rise to sparse solutions. No, it's still robust in the sense that it approximates it doesn't grow larger than +1. So the epitome of a loss function that would not be robust, for instance, would be one that grows exponentially as we move to the wrong side of the decision boundary. So if we have something like that. So that's, let's say, e to the proportional to e to the minus of the score, which I'm not writing down. So the y w transpose x plus b. Then this would be something, this would be something that's definitely not robust, because here the influence of a wrongly classified sample increases exponentially with the distance from the decision boundary. Okay, so the sigmoid loss functions here, they are robust. Okay, and then we come to the Hinge function, which will be at the center of our attention today. First, the central Hinge function. So Hinge in German is Scharnier, wie im Sinne von wie ein Türscharnier, and well, it has that name because it is reminiscent of a hinge. So you know, let's say in a technical drawing, you would indicate a hinge something like that. You would say this is a door in an architectural scheme of a house, and now if you delete this part here, then you indeed and let it, you know, if you let it grow indefinitely on the left-hand side, then you have indeed what is called the hinge function here. And actually, I've plotted several versions of the hinge functions there, namely one that starts to grow just on the wrong side of the decision boundary. So you get zero empirical error for correctly classified samples, and then an error that starts to grow linearly as you are on the or as you move away from the decision boundary on the wrong side. Okay, and this first case is called the central hinge function, and I'm writing that as hinge subscript 0 of the score. And an alternative way of writing the same thing is to say that you take the absolute, well, the notation is like that. So this is a single vertical bar here, single vertical bar there, and a plus, meaning you're considering only the positive part of your argument. Or yet another way of writing the same is to say we're taking the maximum of 0 and minus yi xi transpose w plus b. Now we can again, you know, go through our criteria. Convex or not? It is convex. So thumbs up on that one. Is it robust or not? That's a trick question. It's arguable. So what you see in this plot is that the influence of a sample grows linearly. The influence of a misclassified sample grows linearly with its distance from the decision boundary. So you wouldn't call it, you know, robust in an error sense, but there are much worse functions used in statistics and in machine learning. So, you know, some people would say it's robust, others would say it isn't. So let's say for robustness, let me say it could be worse. It could be better also, but it could be worse. Okay. Now, again, since it goes strictly to 0 for correctly classified samples, it gives rise to solutions that are sparse in the dual domain. And, by the way, it also gives ambiguous solutions. So let's look again at our mantra here. So the central hinge function was the green line here. And Well, if we look at the version space, so of the area that gives 0 empirical error for the linearly classifiable, linearly separable case, the version space is just as large as for the 0-1 loss function. But you see that we now have a single optimum, and we have overall convex empirical error function. That is the case even here in the example that's not linearly separable. Okay, we have a single optimum, which is, however, still degenerate. It's flat at the bottom. By the way, I forgot that part of the discussion for the sigmoids. So the sigmoids compared to the 0-1 loss mean that we now can compute derivatives everywhere. So these are the thin gray lines that you see, or can guess at least, on the beamer. And so we can use gradient descent procedures, and if you make these functions sufficiently smooth, you can even alleviate the problem of multiple minima, and you can also to some extent reduce the ambiguity of local minima. Okay, so that was the central hinge function. And now comes the star of the day. That's the hinge function with a margin. So the central hinge function started growing right at 0. And if we now use a shifted hinge function, and in the terminology of this field, this is just called the hinge function, this has now some margin. So for example, for the red line here, you see it starts to grow at already 0.4 or so. So this would be the margin M. So we have a hinge loss with some margin M. And you can now see why I put a subscript 0 before, because if you now insert an M instead of the 0, we get this new formula here. Okay, let's look at the properties. Just like the hinge loss, this is convex. It is still, so robust. Could be better, could be worse. It also gives rise to solutions that are sparse in the dual domain. And now, depending on the margin, it will have less or no ambiguity. Do you have trouble deciphering my writing? No. Okay. This is the same symbol as we had for the central hinge function. And it means keep the positive part of the argument. So if the argument is negative, then the answer will be 0. And if the argument is positive, then it will return that argument. Okay, now again, let's look at the behavior here for our two toy data sets. So in this case, the red function is a hinge loss with a margin that I have carefully adjusted to exactly lift the ambiguity, yet without increasing the empirical error. So if you look at the red function here, well, it's nicely convex and it has a well-defined local minimum. But if I had made the margin any larger, then this empirical error would no longer have been 0, even though the data set is linearly separable. And on the right-hand side, you see that even when the data is not linearly separable, if we use the hinge loss, we always get a convex function, and if I choose a sufficiently large margin, I also get a unique optimum. So, ideally we would want it to be convex, which it is, really robust, which it is not, sparse, which it is, and less or no ambiguity. So this makes the hinge loss a good overall compromise. And by the way, it's not possible to do any better than that, because convexity and robustness, these bite each other. Okay, so for robustness, I would like to have a function which eventually bends back on itself, but functions like that would no longer be convex. Yeah, you see this function, or the second here cuts the function. So we have to choose, and in practice, people have preferred the convexity over the robustness. Now, as a measure of empirical loss, this is an interesting invention, because note that using this hinge loss, you already get a contribution to the empirical error, even for samples that are correctly classified. So again, the red function is here. The red function is the hinge function with a margin. And for these samples here, we already get a contribution to the empirical error, even though they lie on the correct side of the decision boundary. So you may want to think of this as a preemptive penalization. The classifier already complains if samples even get close to the decision boundary, even if they're still on the correct side. And I would like to argue that this gives you some kind of inbuilt pessimism. And inbuilt pessimism in the sense that we get a non-zero contribution even from observations, even from some observations that lie on the correct side of the decision boundary. So let's say this is my classifier. This is the margin for the samples from the positive class. This is the margin that we would like to keep, or our safety distance that we would like to keep from all samples of the negative class. So these points out here, they make no contribution to the empirical error at all. But let's consider this sample here. It still lies on the correct side of the decision boundary, and even so, it already starts making a contribution to the empirical error. And this contribution grows linearly with its distance from the margin. Now, if the sample lies totally on the wrong side of the decision boundary, of course, we still get a prediction that's now even larger because our distance from the desirable margin has become larger, and so on. So we also penalize, of course, in a similar way samples from the other side. Okay, we will see later that this inbuilt pessimism, is something useful, because unless you regularize classifiers, they tend to overfit. and be overly optimistic about their performance, so you need something to counter that. Any questions so far? Yes? So the question is, why for sparsity, why do I only consider samples with positive score? The reason is that if I look at the empirical error of this situation here, then these points contribute nothing to the empirical error, and those points contribute nothing to the empirical error. So if I wanted to now do something like gradient descent or so on my empirical error, at least at this moment here, I would not even see these samples, and it would in that sense be sparse. And it's especially interesting if you have millions of samples on either side, and if the classes separate well, then it's interesting to be able to express the classifier in terms of only a few samples. And I will give a more mathematical explanation later on. Yes?
How can you make use of sparse? Because each time you optimize the classifier, you have to evaluate whether a sample scores 0 or it doesn't.
So we distinguish between the training and later on the test phase. And if your classifier is sparse in this dual sense, it means that I can specify my classifier. Remember, my classifier is given by the normal vector W and by the shift or B, or the bias B. Then I can express my solution. So I can express the optimal parameters W and B in terms of only a small fraction of the training set. And that is something that I can exploit in the later on in the test or in the prediction phase, because I then, depending on if I operate in the primal or in the dual domain, if I operate in the dual domain, I then need to consider the distance of any new query sample only to those points that were relevant in the specification of the optimal solution. And again, I promise the formulas will follow. Any more questions, comments?
So why keep them at all? Why can't you just W and B?
So why not just keep W and B? That would be operating in the primal domain, so in the feature space domain. And that is entirely reasonable as long as your feature space is of sufficiently low dimension, and it's reasonable as long as you're happy with using just linear classifiers. However, it turns out that if you want to, or the best way to realize nonlinear classifiers with a support vector machine is to operate in the dual domain. That's one reason. And another reason is that it sometimes happens that you have very, very high dimensional observations. So let's say 100,000 features, but you have relatively few, you have a smaller number of samples. And then it's also worthwhile doing all the computations in the dual rather than in the primal domain, simply because you deal with less entities. Okay, so overall what we have is the following problem. We have a training set, and we have a linear classifier, and we have either pre-specified, or we want to find out. Let's say we have pre-specified a certain margin, which I have here indicated. So this would be the margin M. And I put a penalty that grows linearly on all samples that invade the margin. And just to be, totally extra clear on this, so samples can, of course, also be really totally on the wrong side, and then they get an even larger error by having an even larger distance from their margin where they should really be. And by the way, the thing that I've now drawn, it's not the optimal solution, it's just a solution that I've been drawing here. And the goal of the optimization that we will look at after the break is to now find, so given this empirical loss function, given this training set, how do we find the optimum position of the decision boundary? How can we make a computer do that work for us? And we will see how to formulate that as an optimization problem and how to solve that optimization problem.